Good morning, student. In the last part of the video, we have derived the equation of longitudinal wave through a air medium, and if you can remember, we can write the equation of motion as delta 2 eta divided by delta t is equal to Ba divided by rho naught del 2 eta divided by del x square. Okay, this was the equation of motion when a longitudinal wave traveled through air medium, where rho naught was the density of air medium, and Ba was the bulk modulus of air medium, and eta was the arbitrary displacement of a air coulomb. Okay, eta was what? Arbitrary displacement of an air coulomb. Arbitrary displacement of an air coulomb. Okay, so these things probably you would have remembered. Okay, now what I am going to do, I am going to first derive Newton's formula for velocity of sound in air medium, and after that I am going to do the Laplace's correction. Okay, so first let's derive Newton's formula for velocity. Okay, initially Newton considered that the transmission of sound through air medium is a isothermal process. That means there is no local temperature gradient, and the temperature of the air coulombs remain steady when the sound wave propagate through that air coulomb. Okay, so if you can remember, if the pressure and the volume of that air coulomb is P and V, so the equation of motion, if we consider the ideal gas equation, we can write PV is equal to constant. Okay, so this is the PV is equal to constant. It is for isothermal process. Newton considered the transmission of a sound through air medium as a isothermal process. Okay, so if we do P dV plus V dP is equal to 0. So I'm just differentiating P with and then V. So P dV plus V dP is equal to 0, because if we differentiate constant, it will give us 0. Okay, so we can write P dV is equal to minus V dP. Okay, so P is equal to what we can write? dP divided by dV over V. That we can easily rearrange the term. Okay, so minus dP over dV by V, we already know this quantity represent the bulk modulus of the air coulomb, so we can write it as PA. Okay, so this value is equal to P. Now for the value of P is nothing but the value of the atmospheric pressure of the air coulomb, and its value P is equal to, if you remember, 1 how much it was? 1.013 into 10 to the power 5 Newton per meter square. Okay, now if you can see the this quantity Ba divided by rho naught, this has the dimension of the square of the velocity. Let me check what is that dimension. First, let me do a dimensionless analysis for this particular quantity. So if you can do, say, Ba divided by rho naught, what is its dimension? Say Ba dP over dV by V. So volume by volume, its dimension is 0. It's a dimensionless quantity. So basically, we have to consider the dimension of pressure. Unit of pressure. So pressure unit is Newton per meter square. Okay, and the density unit is how much? Kilogram per meter cube. Kilogram into meter cube. Okay, so if we can write it, then Newton meter cube into kilogram meter square. Okay, so these things cancel out, so it will be Newton into meter divided by kilogram. Okay, so Newton is what? Force into displacement. That means Newton is nothing but the force, sorry. Therefore its unit is force is equal to mass into acceleration, so kilogram meter per second square into kilogram into meter. Okay, kilogram get cancelled out, then meter square divided by second square. So it is the unit of square of the velocity. Okay, so basically what we can write, del 2 eta divided by del t square. If we rewrite this equation, how can we rewrite it? Del 2 eta divided by del t square is equal to c square del 2 eta divided by del x square. Okay, and we can rearrange that 1 by c square del 2 eta del t square is equal to del 2 eta del x square. This is more familiar form. This form, the equation of motion used to be written like in this form. Okay, so here we know c is nothing but the velocity of longitudinal wave through air medium. Okay, so what is the value of c now? C square is equal to ba divided by rho naught, and ba is nothing but the atmospheric pressure p. Therefore what we can how now from here we can find the value of c square. Okay, so c will be equal to square root of ba divided by rho naught. Okay, and from isothermal consideration we know that the value of ba is nothing but the atmospheric pressure. Therefore p divided by rho naught is equal to c. So this is the velocity of sound. Sound is a longitudinal wave, is not it? The velocity of sound in air medium. Okay, so this is known as the Newton's formula for velocity of sound in the air medium. Okay, now there is a problem here. The problem is that we know the value of the atmospheric pressure is 1.013 into 10 to the power 5 Newton per meter square, and we know what was the density of air molecule at room temperature. It is about 1.225 kilogram per meter cube. Okay, and if you put this two quantity here, then the value of c, then we can calculate the value of c, and if you plug in these two quantities here, it was found that the value of c is almost 280 meter per second. Okay, but experiment has shown that the value of sound in air medium is almost 330 meter per second. Okay, so Newton's formula for the velocity of sound through air medium is little offset from this experimental value. Okay, so there is something wrong with the Newton's assumption of the Newton's assumption for the propagation of sound wave through air medium. Okay, the problem is that the Newtons considered the process to be isothermal, but basically it's not an isothermal process, but it's an adiabatic process. Okay, that thing I have already told you during the very first class. Why it's not an isothermal process? Because if you remember that when the sound wave propagate through the medium, as you can see, there is a local concentration of air molecules and rarefaction of the air molecule. So the pressure wave will look like that. Okay, so the pressure will not to be a constant quantity, but there will be local increase of the pressure, and somewhere there will be decrease of pressure. So since there is a local pressure gradient, therefore there will be also a temperature gradient, because temperature and pressure, these quantities depends on each other. Okay, so when the sound propagates through air medium, the temperature does not remain conserved for the length of the medium. There will be a change of temperature. Hence, the propagation of sound is not an isothermal process, but it's an adiabatic process. Adiabatic in the sense that the sound wave does not exchange its energy with the atmospheric air molecule. Okay, if it exchanges, or if the sound energy decreases, then it may be possible that we cannot hear what other people speak. Okay, so for that purpose we assume that the propagation of sound through air molecule or air medium is an isothermal process. Adiabatic process, and for adiabatic process we are going to use this kind of equation: P v to the power gamma is equal to constant, where gamma is nothing but the ratio of Cp by Cv, that you may have known. Okay, so basically I am going to use this kind of equation of state for the propagation of sound through air medium, and from that I am going to derive the velocity of sound through air medium, and this formula is known as the Laplace's formula. So the name of the topic is Laplace's correction to the Newton's formula. Okay, so let's do that. Okay, so now let's write the equation of motion as P v to the power gamma is equal to constant. And similarly, we can do the differentiation of P and V. So what we will find, P gamma to the power v to the power gamma minus 1 into dv plus dp into v to the power gamma is equal to 0. Okay. Okay. So we can write P v to the power gamma, this thing you can write P v to the power gamma into gamma v to the power minus 1 into dv plus v to the power gamma dp is equal to 0. Okay, this thing we can write. Okay, so far everything is okay. So v to the power gamma is here, v to the power gamma is there. We can cancel out gamma p dv divided by v plus dp is equal to 0. This thing we can write. So just cancel out this term and this term. Okay, gamma p dv v to the power minus 1 means 1 by v plus dp is equal to 0. Okay, so gamma p dv by v is equal to minus dp. Okay, so gamma p is equal to what we can write, minus dp dv over p. Okay, so this quantity is nothing but the bulk modulus of air molecule, air coulomb. So this is the value of BA. So if we consider the transmission of sound as a adiabatic process, then we can get the value of BA is equal to gamma into P. Okay, so now what will be the value of C? C is equal to, as we know, root BA divided by rho naught. So put this value, gamma P divided by rho naught. Okay, so now root gamma into root P by rho naught. Okay, so root P by rho naught, we already know its value is 280 meter per second. Okay, this factor should be multiplied by root gamma. Okay, and we also know the value of gamma. Gamma's value you can find in any textbook, and for diatomic molecule, its value is around 1.40. Okay, so you have to multiply it by square root of 1.40. You do the calculation and you will find the value of sound will be almost 330 meter per second. This is what we measure experimentally. Okay, so this experimental proof means that we have to consider the propagation of sound through the air medium as a adiabatic process. It's not an isothermal process. So Newton was little wrong in his consideration for the propagation of sound through air medium, and Laplace has finally corrected this term, and we got whatever the value we measured experimentally. Okay, so this process, this process is known as the Laplace's correction of Newton's formula. This you can find in any textbook. I mean, it's very common thing, and probably you have studied it during your HS first year. Okay, so so far this is okay. In the next part of the video, I am going to discuss about the energy which is carried by the longitudinal wave, and also the intensity of the sound wave. Okay, we have to know how much intense the sound wave is. Okay, and how much energy it's carrying. Okay, so in the next part of the video, I am going to discuss these two very important topic of consideration. Okay? Thank you.